So now finally we can look into how to solve these kinds of differential equations. So this is the compact way of writing it, and then here's the full deal. So it's a differential equation system, two unknown functions, x and y, both functions of the same variable, which we can call t. And we could call this a linear homogeneous system of differential equations with constant coefficients. So it's linear because you can write it kind of in this form. Lx equals 0, where by x I mean this function of t. And it's homogeneous because of the 0 on the right-hand side. And if, in case you forgot, the way to get it into this form is to view L as being derivative with respect to t operator minus application of the matrix A operator. And this long way of writing things comes from realizing that when we write vector x of t with this vector arrow above it, then that is referring to actually two functions packaged together. So always pay attention to when there's a vector arrow here. That means there's two functions in there, or many. That's the beauty of this whole linear algebra way of writing things, is that whether you're dealing with two things or 20 things in a 20 by 20 matrix, all the notation looks the same. By the way, what you'll see in the textbook is going to be a bold X, like kind of like that or something, as opposed to like a scripty non-bold X. But that's harder to do with handwriting. That's why I use the vector symbol. So those are being used to mean the same thing. Okay, so this is the kind of differential equation we're looking at, and it's something you can write like this. So you can view it as a linear, where L is a linear operator, this one. So you can view it as a linear homogeneous differential equation. That means all of those things that we learned about linear homogeneous differential equations from chapter 2, and all the things you learned about linear systems pretty much in Math 4a, those things apply. So the goal to find a general solution, what we want is 2 or n, if this is an n by n system, but let's do everything with 2. We need two linearly independent solutions. So we're going to call those like x1 of t and x2 of t. And remember, I'm writing x with a vector symbol, so that means each one is actually two functions. That's a total of 4 functions, right? Like x1, y1, and x2, y2. So we want these two linearly independent solutions, and then the general solution will be this. And I keep saying this, the more you can package together x of t and y of t, like this is a vector of functions, right? It's really two functions, x of t and y of t. The more you can package things together, the less confusing this will be. So when you package together the two functions in here, x of t and y, x1 of t and y1 of t, and then here x2 of t and y2 of t, then when you write the general solution like this, then you can see very clearly how the unknown constants, or these free parameters c1 and c2, you can see very clearly how there's only 2 of them and not 4 of them. So just having two initial conditions, like something for x of t and something for maybe for x of 0 and something for y of 0, or just one initial condition, if you write it like this maybe, would be enough. Okay, so the goal is to find a general solution, because we want to be able to satisfy any initial condition setup. And we're seeing that to do this we need two linearly independent solutions. So where do we get linearly independent solutions? And here it comes. So this is where the solving the eigenvalue problem for A is going to come in. If V is an eigenvector for A with eigenvalue lambda, then define a function, a vector-valued function, so two-component function of t like this, e to the lambda t times the vector v, then this is a solution to our differential equation, x prime equals ax. So this is why we were concerned with solving the eigenvalue problem for A. And this is the key to everything, basically, in Chapter 4, and with solving linear systems of differential equations. So this is where we will get our linearly independent solutions that we need. Okay, so let's see that this is true. It's very easy to check. So to check that this is a solution to this differential equation, all I need to do is plug this in to the differential equation and verify that the left-hand side equals the right-hand side, right? Well, let me take the derivative. So the v is a vector of constants, right? This is just whatever this eigenvector is just going to be a vector of constants. All the time dependence is in the scalar out in front. This is how the derivative ends up working. You get the chain rule, and the v just sits there. So lambda came down. So that'll be the left-hand side. If you substitute this particular function into the differential equation, this will be the left-hand side. It'll be the x prime. So this ends up being lambda e to the lambda t v. And what does this end up being? Ends up being a x. X is this. So e to the lambda t v. Now this is matrix times scalar times vector. So the scalar actually doesn't matter what order you do it in. If you're multiplying two matrices by a vector, then we've seen before that the order definitely matters. But a scalar can just move in and out freely. And you can just do this. So then look at AV. What's AV? Well, this is the whole point, is V is an eigenvector for A with eigenvalue lambda. So AV is actually something very simple. It's just lambda V. And so you see the left-hand side is lambda e to the lambda V, and the right-hand side is also lambda e to the lambda V. So this is how we get our two linearly independent solutions. If we can do it, this is how it'll be done. By solve the eigenvalue problem for A. So, okay, this is kind of written backwards. Usually you start here, right? You don't start with just a random matrix A, but you start here. You have your differential equation. Then, to get two linearly independent solutions, solve the eigenvalue problem for A. Then you get a collection of eigenvectors and eigenvalues. And then, by constructing these functions of t out of your eigenvectors and eigenvalues, you would be constructing solutions to the differential equation. So this principle here, this relationship between the eigenvalue problem for the matrix of coefficients in a differential equation and the solutions that you can construct, this is the key to all of Chapter 4. So if you end up remembering one thing from the second half of this course, I would say this is the thing to remember. Okay, so again, going back here, our goal here is to find a general solution. To do this, we need two linearly independent solutions. That's because we expect the solution space to be two-dimensional. And we now have a technique for generating solutions, but we're not guaranteed that it will always generate two linearly independent ones. Our technique for generating solutions is solving the eigenvalue problem for a matrix, for the matrix of coefficients. So anytime you find an eigenvalue-eigenvector pair for your matrix of coefficients, that will get you one solution to this. Of course, you can always scale an eigenvector, like you can multiply an eigenvector by 2 and that will give you another eigenvector, but that does not get you any more here because you need two linearly independent solutions. So you really care about finding linearly independent eigenvectors in the end. Now, can you always do that? Well, it turns out you can always find an eigenvector as long as you at least allow for complex eigenvalues and eigenvectors. If you allow for non-real answers, then it turns out you can always find an eigenvector and an eigenvalue. So you always get an eigenvector-eigenvalue pair, so you always get at least one thing to go here. But you've seen that some matrices are defective, and you end up not getting a second eigenvector-eigenvalue pair. So then what do you do here? Well, there's still a way to deal with that, and we might get into it. It's like later in the chapter. But mainly what I want to focus on to begin with is the situations where the typical situations, which are where you do get a full set of linearly independent eigenvectors for your matrix. And that leads you to a full set of linearly independent solutions. Then what's going to be really interesting and quite fun in this chapter is to look at what those solutions look like in the phase plane, what do the solution trajectories do, and how we can predict what they're going to do just from looking at eigenvalues and eigenvectors. Okay, so that's actually pretty much all there is to the technique, but that was all pretty abstract, so let's solidify that with some examples in the next video.